one of the areas that VCAR constantly recommend that teachers address is the concept of lactate tolerance and the concept of lactate removal and the lactate inflection point, because questions are constantly coming up in this area and students are still having a little bit of a trouble differentiating or telling the difference between the two. So while it might sound relatively self-explanatory, the definitions, let's go through them. Lactate removal refers to the efficiency of the body to remove lactate and the associated hydrogen ions. So we know that we always have lactate in our body. It's produced by the anaerobic glycolysis system, and because all energy systems are always working, we always have some. Likewise, we always have some hydrogen. The problem is when hydrogen or lactate build up and we're not able to remove it as fast as it's being produced, because that causes fatigue. It causes fatigue due to an accumulation of metabolic byproducts, and it's specifically the hydrogen ions that cause fatigue because they change the pH of the cell. They make the cell, and the muscle cell we're talking about here, more acidic, and they interfere with enzymes, glycolytic enzymes that are responsible for helping glycogen break down. And if we can't get that glycogen to break down fast enough, we're not going to be able to produce ATP or resynthesize ATP at the same rate. And so we're not going to be able to produce force at the same rate, and that's fatigue. Now, our lactate and hydrogen are removed via the aerobic system, and we'll talk about that a little bit later. So it makes sense that lactate removal is going to be enhanced via training that aerobic system to be stronger so that it can deal with and remove those metabolic byproducts at a faster rate. Lactate tolerance, on the other hand, is working when you have an accumulation of lactate and hydrogen in the body and you're still able to perform. So it's being able to physically and mentally deal with those feelings of acid in the muscle, that acidic environment in the muscle, and still able to push through. So by exposing yourself to these sort of environments, by exposing yourself to anaerobic type training when you're going to have a build-up of lactate and hydrogen, you're going to be better at dealing with those feelings of it in your body. So it's predominantly enhanced via anaerobic training. So the reason why we're looking at this, some of the comments from VCAR, and this one's from a couple of years ago, this particular comment is specific to a question, but I want you to just have a look at the first line and the last line. So lactate tolerance and the lactate inflection point continue to trouble students. Remember, if VCAR spot a little bit of a weakness, they'll continue to ask questions in this particular area. And just look at that last sentence, because we're going to focus on this as well. Training methods that increase lactate inflection point or increase the body's ability to remove lactate are going to be aerobic-based activities or aerobic training. Whereas training to increase lactate tolerance, so that's dealing with those feelings of lactate and hydrogen in the body, so it's going to be predominantly anaerobic training. And they say that they're being poorly understood by many students. So let's try and break this down a little bit more. Firstly, let's have a look at this concept of how we get lactate and how we remove it as well, and hydrogen. So anaerobic glycolysis is what we're looking at here, and we know that glycolysis is the breakdown of the fuel glycogen to glucose, and I've just jumped in at the next step, which is where it's turned into pyruvic acid. Now, pyruvic acid can either be broken down completely using oxygen via the Krebs cycle and the electron transport system, or if we need energy quickly, it's going to be broken down via the anaerobic glycolysis pathway or the lactic acid pathway. So pyruvic acid in the cytoplasm of the cell gets broken down into lactic acid. As soon as lactic acid is produced, it immediately splits, or the term you might be familiar with is dissociates into two, into lactate plus into hydrogen. Now, how the body gets rid of this, it gets rid of this lactate by diffusing from the working muscle into the blood, and there it will be taken up by other muscles, and that's called the lactate shuttle, or it will be taken back to the liver where it's going to be converted back to glycogen as a fuel use. Hydrogen ions, on the other hand, mostly get removed or buffered via the aerobic system within the muscle, and it's this build-up that we know causes fatigue. So let's have a look at this concept, because at the moment we're talking about the lactate removal, and we're going to link that into lactate inflection point. So when lactate production is matched by lactate clearance, and it's the aerobic system that is clearing that lactate, we're in what's called a steady state. The aerobic system is always going to be dominant at steady state, and you should be thinking of steady state when oxygen supply is matched by oxygen demand. And lactate inflection point is the maximum intensity when lactate production is matched by lactate clearance. It's the highest steady state that we can hold when the aerobic system is dominant. The anaerobic glycolysis system is very much contributing, as all energy systems contribute, to energy production or ATP resynthesis, but we're holding that steady state with the aerobic system dominant. So this concept of steady state when lactate production is matched by lactate removal. As fast as lactate is produced, lactate is removed. So we're in a balance, and hopefully you can see that that's a steady state. Which energy system is dominant at a steady state? It's the aerobic energy system that's dominant here. So what we're going to look at this here is we're going to look at it with the concept of lactate inflection point. And this graph you'll be really familiar with now. We're looking at what's called an incremental treadmill test, where you increase the running speed, kilometers per hour, along the x-axis, and we're looking at blood lactate in millimoles on the y-axis. And you can see that there's always going to be a little bit of an increase in blood lactate as you increase intensity, because the demand for ATP increases, so the contribution from energy systems increase as well. And there comes a point in time though when lactate production is only just matched by lactate clearance. So at any intensities greater than this point, lactate inflection point, the blood lactate is going to accumulate faster than it can be removed. We are no longer in steady state. We get an increase in energy production via the anaerobic glycolysis system, and the aerobic system, while still dominant, is not going to be able to remove that lactate, the hydrogen, as fast as it is produced, and we will suffer from fatigue due to the accumulation of metabolic byproducts. At that lactate inflection point, the aerobic system is the dominant energy system. So here we're looking at 11.8 kilometers per hour on a treadmill. And if you've had a go at running on a treadmill before, you'll know 11.8, that's probably quite a low point to be able to hold for a lactate inflection point. Maybe this person might not be super fit, but that's the point that they can hold before you get that really big kick or that really big change in blood lactate. So if you just look again at that lactate inflection point on the right-hand side, it's the maximal intensity when lactate production is matched by lactate clearance. It's the highest steady state we can hold, and VCAR have given us the value of approximately 85% of max heart rate. That's going to be for someone who's reasonably trained. Someone who isn't trained might have a little bit lower than that. Anywhere from 70 to 85% tends to be the values that VCAR like to talk about, but for a trained athlete, perhaps around 85% of maximum heart rate is what they can hold. So our aerobic type training is what we want to do in order to strengthen the aerobic system so that it can remove or enhance the removal of lactate and hydrogen. If we have a look at that type of training and the benefits of training, 2 points, but the second one's the one we're going to talk about. So of course aerobic training is going to assist in energy production in longer or for longer duration events because it's going to be more efficient. However, what it does do is it delays lactate inflection point. And when we mean delay lactate inflection point, it means that on a graph we have a right shift, and I'll show you that in a second. It enhances lactate and hydrogen removal. So the body is more efficient. It can produce energy more efficiently using the aerobic system, and the aerobic system can better remove lactate and hydrogen. So both of those mean that we're going to be able to work at a higher intensity for longer. So let's have a look at two graphs. So the one we were looking at before is the red one, and that's actually after training on this particular graph. And the blue one that we're looking at is before training. And that's what I was talking about before when I was talking about a right shift. That as you undergo aerobic type training and your aerobic system becomes more efficient, it's going to be able to produce energy faster, and it's going to be able to remove those metabolic byproducts at a faster rate as well. As such, you're going to be able to run at a higher intensity for longer. And that lactate inflection point, remember, refers to the highest steady state that you can hold. So if you're looking at a half marathon or a marathon, the blue athlete is going to be able to run at 10 kilometers per hour, and that's the highest steady state that they can hold. and the red athlete is going to be able to run at 11.8 kilometers per hour. So the red athlete is going to be the faster athlete, and they're going to perform better due to the increased efficiency of their aerobic system. And when we talk about aerobic type training to actually enhance this, we might talk about continuous training, we might talk about fartlek, or perhaps long interval type training. The training is going to be best if it's specific. So the running type training is going to be best in this particular case. So when we get a greater lactate production than removal, so you can see in these scales we're being weighed down with lactate here, and the removal doesn't balance, we're not in a steady state anymore. When we're not in a steady state, we're not going to be able to hold the intensity for a long time because we're getting that accumulation of the metabolic byproducts. And what we're talking about now when we're not in steady state is we're talking about the individual's ability to tolerate lactate, to push through in that last 100 meters, for example, of a 400 meter race, being able to push through that, to tolerate those feelings being produced in the muscle and still be able to perform. So now what we're talking about when we're talking about tolerance is we're talking about the athlete working up perhaps at these intensities. And it's not going to be the situation with lactate tolerance necessarily that you undergo an incremental running speed, but perhaps they might start out running at these really high intensities here. So it's not that it will follow this pathway per se, so that's not the purpose of showing you this. The purpose for showing you this is to say that if the athlete is running at 17.8 or 19 kilometers per hour, they're going to have a blood lactate level that is far higher than what can be dealt with in a steady state. So their blood lactate is going to be higher than their lactate inflection point, and they're not going to be able to hold that intensity for a long period of time. However, by training the body at those intensities, they're going to be able to learn to deal with the feelings of lactate, and as well as training in those particular areas, they will have ability to buffer the lactate faster as well. So it sort of goes both ways, that you learn to deal with the feelings, but also your body can process it a little bit faster because you've practiced having those high levels within your body. So let's have a look at training lactate inflection point, and let's have a look at some questions here. So why do blood lactate levels remain relatively stable during submaximal exercise? And what they are really wanting you to do here is say that lactate production is matched by lactate clearance. I'll just give you a moment perhaps to have a look at these questions, answer them before I race ahead, and then we'll go through the answers. So just 30 seconds to have a look and see if you can answer them. Okay, let's go on to B. Identify a training method that will be most beneficial for increasing an athlete's lactate inflection point. So we're talking about removal of lactate now, LIP. So we're thinking about aerobic training, continuous, fartlek, perhaps long interval training, not anaerobic training. If you said short interval training, that's not right. That will help with tolerance, but it's not going to help with the increased removal. That is going to be via aerobic training. When you're looking at C, which of the graph shown reflects the change to LIP and VO2 max after 12 weeks of the type of training identified in Part B? 12 weeks is an ideal training program time, and that's an important point that they've put in there. So hopefully you said C, the dotted line, pre-training. Just like the graph that we looked at before, you've got a right shift there, and the body's going to have an increased ability to remove lactate due to the aerobic training there. Let's have a look at the justification that they put in there. So we've gone through those first questions. The body is able to remove lactate at a similar rate as it is produced. Different types of aerobic training. Graph C. So 29% of the state got that one, or perhaps not got that one wrong, it's out of 4, isn't it? But 29% of the state got 0 at least. Let's have a look at this answer here. With 12 weeks of training, you're going to have chronic adaptations to all different body systems: cardiovascular, respiratory and muscular system. So therefore, fewer hydrogen ions are produced, which will allow the body to work aerobically at higher intensities. So that means the body is going to be able to work more efficiently using the aerobic system. It's going to be able to produce energy at a faster rate using the aerobic system. It's going to be able to remove lactate at a faster rate and hydrogen at a faster rate. So that's going to have a right shift. And I think that's an important point there where it says fewer hydrogen are produced, because when we've got a more efficient aerobic system, it can produce energy at a faster rate. So there's less reliance on the anaerobic glycolysis system as you increase your intensity. So that's an important point to add in when we're talking about training for our lactate inflection point. All right, this is a pretty challenging question. As part of the Australian National Record Holders training for the 100 metre freestyle, the swimmer trains at 75 to 90% of their VO2 max. So we've previously been talking about heart rate, and I know I've included this slide on a couple of different, or this question on a couple of different slides that we've had through these tutorials, but it's an important one. Not many students got it correct. So if we're looking at 75 to 90% of VO2 max and we're thinking about a 100 metre freestyler, wonder if you're thinking that it's going to be more of an anaerobic or more of an aerobic type event there. Discuss why a 100 metre swimmer trains at this intensity and how this intensity affects performance and blood lactate levels at the end of a 100 metre swim. So firstly, we need to work out, well, 75 to 90% of VO2 max. We know that it's around 85% of heart rate max that is lactate inflection point. So let's have a look now at what 75 to 90% of VO2 max is. And you can see if we're looking at our VO2 max, we're looking at somewhere between T3 and T5. And these are just, T stands for training zones. Different training zones achieve different outcomes. So if we're looking between T3 and T5 in terms of our VO2 max, look at what's happening to our heart rate between 85 or above 85% all the way up. If we're working at 85 or above in terms of our heart rate max, we're going to be working above lactate inflection point. So we're working predominantly anaerobic, and our lactate production is not going to be matched by our lactate clearance. So why are they going to train at that intensity and how this intensity assists performance? So discuss why 100 metre swimmer trains at this intensity and how this intensity affects performance and blood lactate levels at the end of a 100 metre swim. It's worth 4 marks. Let's see what the assessors had to say about that one. 57% of the state, firstly, got 0. So what you'd need to say, at this intensity, the swimmer is training above that lactate inflection point. So that's the steady state that they can hold, and therefore cannot clear the lactate at the same rate in which it is being produced. If you see lactate inflection point or the opportunity for lactate inflection point within a question, make sure you define it, because quite often it's worth a mark, and in this particular instance it was. So you needed to say for 1 mark that the swimmer is training above their lactate inflection point, and then you needed to define lactate inflection point. So lactate accumulates, but the training increases lactate tolerance, and that was really important as well. The swimmer is able to work at a higher intensity for longer. So now we're talking about the outcome. And the other important point as well, because it asks specifically what about blood lactate levels at the end of a 100 metre swim. Blood lactate levels will be through the roof at the end of a 100 metre swim. There's no way you'd be in balance. So if you look at that last point there, producing high blood lactate levels at the end of the race, that would be really important as well. Just like we've talked about a question between blood lactate levels at the end of a 400 metre event for a trained versus an untrained person, that trained person is going to have a far greater blood lactate level because of their ability to tolerate lactate production. So let's go back and have a look at what you'd need to say. You'd need to say they're training above lactate inflection point and define it. You'd need to say that it accumulates, but that training increases the tolerance, and therefore you can work at a higher intensity for longer, producing higher blood lactate levels at the end of the race. It's a tough question. Only 2% of the state got all 4 marks there. And just to finish off with this point here again, we'll come back to lactate tolerance and the lactate inflection point continue to trouble students. Most thought that training at or above LIP will increase LIP. You need to be at or a little bit below. what you need to be able to do is, and this is specific to a question, so need to identify from the data that the athlete will be working above lip. So this is for the question that we just spoke about, and therefore producing lactate at a faster rate than it can be removed. The body learns to tolerate the increased levels of lactate, allowing the athlete to continue to generate ATP anaerobically, which is at a faster rate and allows them to swim at a higher intensity. So anaerobic training is going to increase your anaerobic or your tolerance, your lactate tolerance. Therefore, you are going to be able to work at a higher intensity for longer, dealing with those feelings, and therefore produce ATP at a faster rate. In order to increase lactate inflection point, we need to undergo aerobic training, and to increase lactate tolerance, we need to go anaerobic training. Hopefully